Effect studies were carried out on a wide variety of near-surface nuclear detonations to increase knowledge of the basic effects of megaton range shots and the effects on structures and materiel, especially of megaton range shots. To extend the knowledge of basic effects of nuclear detonations, 3 programs were instituted on Operation Hardtack: underground studies of acceleration, displacement, pressures, and shock spectra; radiation studies of neutron flux and fallout from megaton devices; electromagnetic studies of pulses from nuclear detonations and ionospheric effects of surface detonations. Ground motion measurements were made on 2 surface bursts, the 17-kiloton Cactus and the 1.4 megaton COA detonations. Emphasis was on obtaining measurements in high overpressure regions for use in the design of hard protective structures. The effect of soil type and weapon yield on ground shock was of particular interest. Participation in Cactus supplied low-yield coral soil data for comparison with results obtained in Nevada soil from shots of similar yield. COA provided high-yield data for comparison with the low-yield Cactus data obtained in similar soil. Underground accelerations and displacements produced by COA and Cactus were measured in regions where air overpressures were up to 900 psi. COA measurements, in particular, were at 3 ranges from 2,000 feet to 4,000 feet from ground zero and at depths down to 100 feet. Underground pressure measurements were made with flexible drumhead gauges. These were buried at depths from surface down to 20 feet at the 200 psi range on both shots. Canisters with vibrating reed-type gauges were installed with their tops flush to the ground surface and inside flexible arch structures at overpressure ranges from 75 to 200 psi. The response of these gauges to ground shock is being used to broadly delineate the responsive structures or instrumentation to the same shock environment. An air blast line was installed to provide air overpressure measurements for correlation with the ground shock data. To complete the specification of the ground shock environment, crater measurements on both shots were taken by lead line and photographic techniques. On the COA shot, at 2,000 feet range, just 150 feet outside the crater, peak vertical acceleration of 1120 G was recorded at 1 foot depth. Peaks decreased rapidly with depth to 68 G at 10 feet and then slowly to 8.4 G at 100 foot depth. Vertical accelerations at 3,150 feet range show similar decrease with depth from 441 G near the ground surface to 1 G at 100 foot depth. Maximum vertical acceleration on the Cactus shot was 616 G at 400 foot ground range and 1 foot depth. Cactus peak vertical accelerations also showed rapid decrease with depth. On both shots, peak vertical acceleration showed a more rapid decrease with depth than at Nevada at similar air overpressure ranges. Horizontal ground accelerations on both shots were higher than those observed at similar air overpressure ranges in Nevada. On COA, peak horizontal accelerations at 2,000 feet range varied from 40 G at 10 foot depth to 51 G at 50 feet depth to 5.6 G at 100 foot depth. Observed acceleration records did not follow as simple a pattern as previously observed from airbursts at NTS. Nevada acceleration traces are more readily related to the shape and strength of the air blast wave, which generates a ground shock as it arrives at a location. The EPG records of the hardtack shots, Cactus in particular, are much more complex. The high seismic velocity characteristics of the coral soil causes early arrival of refracted and direct Earth-transmitted energy, which in many instances masks effects due to the local air blast slap. Relative displacement measurements between the ground surface and the 50 and 100-foot depths on both shots showed smaller displacements than expected from Nevada results. The largest was less than 3 inches. Underground pressure measurements taken with flexible drum heads show pressures a few feet below the surface are considerably lower than surface air overpressures. However, at 10-foot depth, pressures begin to increase. On cactus in particular, a pressure of 500 psi at 20-foot depth was recorded, twice the surface overpressure. It is believed the abnormally high underground pressures are due to the effects of large amounts of groundwater in the soil. Measurements of air blast phenomena, which were made over extended blast lines for cactus and koa, did not indicate a precursor formed on either event. Waveforms generally showed sharp rises, but were more disturbed for cactus than for koa. Peak pressures obtained with self-recording gauges compared favorably with pre-shot predictions, but those measured by electronic gauges at close-in range for correlation with underground phenomena did not. Furthermore, waveform characteristics at these locations were quite different for the two events. Until further analysis is made, caution should be used in predicting underground structural damage at short ranges. Ground motion results indicate soil type and device yield play an important role in determining underground motions. Correlation of ground motion with air blast data is in progress in an effort to produce scaling relationships. Simple scaling relationships to give ground motion for a particular soil and weapon yield are not apparent. The radiation program studied neutron flux and fallout for megaton range bursts. The objectives of this program were to measure the complete neutron spectra as a function of range and to determine the relative contribution of certain radionuclides to both local and worldwide fallout resulting from megaton land and water service detonations. Instrumentation for the neutron flux dose measurements consisted of threshold activation and fission detector foils exposed along a single non-radial line from 900 to 4,100 yards from ground zero. This instrument line was used on 2 shots with predicted megaton range yields to document neutron flux spectra and neutron dose as a function of distance. Although only limited data resulted because the radiological situation prevented early recovery of the detectors, successful measurement of neutron flux and spectra were made for a number of ranges. The measured neutron doses were found to be lower by a factor of 2 than the TM23-200 predictions. In the study of radioactive fallout, 2 methods of sample collection were programmed. First, early cloud sampling by rockets. And second, residual cloud and fallout sampling by B-57 and WB-50 aircraft. Because of technical difficulties during pre-shot testing and early participation, the rocket sampling was canceled. The aircraft sampling program was successful on all shots in which the project participated. The B-57s collected gas and particulate samples from the residual cloud, while the WB-50s obtained downwind fallout samples at an altitude of 1,000 feet for various times following the detonation. Samples obtained from this program are presently undergoing detailed analysis and study in various laboratories, and any conclusions must await the completion of this work. Electronic studies were made on two effects: the electromagnetic pulses and disturbance of the ionosphere as a result of nuclear detonations. To record the waveform of the electromagnetic pulse, two stations, positioned 100 miles and 460 miles respectively from the burst point, made broadband measurements from 0 to 10 megacycles. Signals received by vertical probe antennae were fed into oscilloscopes, and the resulting waveform was photographed. These studies were made on 7 different shots, including the Yucca balloon detonation. From a comparison of this information with actual shot data, it is hoped that the electromagnetic pulse can be used to approximate total yield when the time and location of the nuclear detonation is known. To study the disturbance of the ionosphere as a result of surface detonations, a C4-type vertical ionospheric sounder was installed at Kusai Island, 460 miles south of Eniwetok Atoll. Similar equipment was located at Wake Island. These sounders emit 50 millisecond pulses at 60 pulses per second, with frequencies from 1 to 25 megacycles. After the signals are reflected from the ionosphere, the received signals are displayed on oscilloscopes as traces. These traces were then photographed for later analysis. The results of this experiment agreed with similar studies made on Operation Red Wing. The energy responsible for the first ionospheric disturbance travels at about 12.5 miles per minute. The energy responsible for a second disturbance travels at about 8 miles per minute. In addition to the basic effects program, other experimentation was conducted on material reactions to nuclear detonations. These studies were concerned with aircraft structural tests, underground structures, electronic fuse components, thermal studies of skin simulants and uniform materials, and material ablation. In the aircraft structural effects program, the delivery capabilities of 3 aircraft types were examined. The B-52 first tested on Operation Red Wing, and 2 Navy carrier planes, the A-4D and FJ-4, both of whose responses to inputs from low-yield nuclear bursts were measured during Operation Plum Bob. The objectives of this program were to measure the structural responses of these aircraft when subjected to the effects of high-yield nuclear detonations. The particular response data sought on the B-52 were side loads imposed by the effects from nuclear explosions in order to determine the aircraft's capability for multiple delivery strikes, where blast and thermal loads could be received at any angle from weapons delivered by other aircraft. Overpressure input measurements for the B-52 proved to be approximately 10% less than predicted. The hardtack test results indicated that the analytical value for bending moment at wing station 1178 was a reliable guide to the capability of the wing. Fin and stabilization load data indicated that pre-hardtack correlation factors were appreciably below measured values obtained at some orientations. A more extensive analysis is now being performed to define the effects of overpressure diffraction loading and orientation on the fin and stabilizer responses. There was no evidence of damage from thermal energy or blast effects as a result of participations in the side-loading program. To aid in structural analysis of the A-4D and FJ-4, a method was employed for measuring transient input conditions on the wing as it was engulfed by the shock wave. This procedure utilized data obtained from several series of chordwise pressure pickups. Correlation data were obtained to examine the diffractional pulse and confirm the structural analysis by progressing from the shock waves measured overpressure input to measured aerodynamic reaction resulting from this overpressure, and hence to measured dynamic response of the structure. Using a conservative factor of 10%, the calculated input overpressures gave good correlation with the measured results. Satisfactory wing chordwise pressure distribution data were obtained. The data are sufficient that, from a careful analysis, the separate effects of overpressure propagation and gust velocity approaching from the trailing edge can be obtained. Although thermal input predictions were conservative, thermal responses correlated well. One participation, shot Walnut, resulted in minor thermal damage on the two FJ-4 aircraft which participated, with blistering on the underside, burning of seals between movable and fixed control surfaces, as well as blistering on the rubber surface on back of the central pod and on the rubber seals on the bottom of the fuselage. The underground structure study was made in conjunction with the ground motion studies previously shown. This program was carried out on Hardtack in order to provide input data for designers of hard protective structures. Previous studies have been confined to low yields and Nevada soils. These structures, prefabricated corrugated steel flexible arch structures, were the targets for design studies on underground structural response to air blast and ground shock, the next step beyond the Priscilla findings of Operation Plumb Bob. Positioned in non-drag sensitive earthwork configurations of coral sand, they actually simulated balanced cut and fill buried structures. Inside the structures, floor slab accelerations, arch deflections, and internal pressures were measured. 3 of the arch shells were tested in the 80 to 180 psi peak overpressure region from COA's 1.4 megaton surface detonation, a long-duration loading test. Another was placed in the 90 psi peak overpressure region from the Cactus 17 kiloton burst to permit correlation of the effects of short-duration blast loading in a similar configuration. The Cactus tested structure, shown here, a 25-foot span by 48 feet, arch structure of 10-gauge metal, partially collapsed on the side away from ground zero. The collapse was apparently initiated by bearing failure of the shell plates at a bolted horizontal seam, about 5 feet above floor level on the collapsed side. A similar structure, subjected to 78 psi from shot COA, suffered a complete collapse symmetrically about the crown. The same effect was observed on a nearby 38-foot span by 40 feet arch structure of 1-gauge metal under 100 psi peak overpressure from COA. At 180 psi, another 25-foot span 10-gauge structure collapsed until the crown touched the floor. High radiation levels on the COA exposed structures delayed complete recovery operations for a number of months. Pending full analysis, it appears that the Plumb Bob design recommendations for this type structure are still valid. To establish design criteria for ICBM and other massive reinforced concrete structures under blast loads, thick reinforced concrete slabs were placed in COA's shot's high-pressure regions, 175 to 600 psi, for dynamic behavior study. For this test, 30 slabs with reinforcing in one direction and 15 slabs with reinforcing in 2 directions were cast with spans of 6 feet and varying depths up to 5 feet. The slabs were placed flush with the ground surface to study flexure and shear strength, both with and without shear reinforcement. The results indicate that the resistance of the slabs to high blast pressures, particularly in respect to diagonal tension, was much greater than expected. After the high radiation level died down, the slabs were removed and examined to determine the magnitude and character of the permanent deformations. The data is currently being reduced and analyzed. One vital project expanded the Plumb Bob study of the effects of nuclear radiation on electronic fuse components and materials. The tests were conducted under simulated tactical and storage conditions, in which instrumented corporal missile fuses and allied components were buried in proximity to several bursts of kiloton strength. Magnetic tapes recorded the data for later recovery and reading. Fuses and numerous types of components were subjected to neutron exposures of from 10 to the 12th to 10 to the 14th neutrons per square centimeter, and gamma dosages of from 10,000 to 100,000 Roentgens. Since this project sought information on such questions as whether a missile during a multiple attack would function properly when a nuclear weapon burst nearby, it is noteworthy that many important changes in the electronic gear under test were observed. For example, some transistor parameters underwent transient changes 84 times their initial value without ensuing permanent damage. Plate currents of vacuum tubes changed up to 120%. Resistors exhibited decreases in resistance of from 10 to greater than 20% for periods of a millisecond. The corporal fuse system exhibited transient disturbances which indicate a high probability of premature firing when exposed to radiation doses as low as 10 to the 12th neutrons per square centimeter and 10,000 Roentgens of gamma. In the thermal radiation study exposing skin simulant specimens, both bare and covered with uniform materials, the objective was to validate laboratory methods of determining the degree of protection afforded by uniform materials under actual long-pulse megaton-type exposures. It was found that the field test results on the higher yield weapons differed in some respects from Naval Material Laboratory's predicted results. These differences indicated the possibility of a discrepancy between the laboratory's simulated thermal pulse as well as lower effective radiating temperatures of larger yield weapons. In a study to determine the rate of ablation of materials, metal specimens were mounted on a 100-foot tower within the shot cactus fireball volume. Recording equipment and thermocouples were buried at various depths within the specimens to determine the ablation rate. Another specimen within the fireball volume was designed to measure the velocity of sound from which the temperature within the fireball could be calculated. The method used involved recording equipment and transducers to pick up the pressure pulses from a series of small HE charges set off at sequential times after time zero. Data were obtained and recorded. However, thorough laboratory analyses must be completed before any conclusions can be drawn. The effects programs we have just reviewed were all successful in gathering a vast amount of data, much of which is yet to be analyzed. Ultimately, the extent of knowledge concerning the effects of megaton detonations will be greatly advanced. A brief summary of these programs indicates that soil types and yield are important in determining underground motions. However, simple scaling relationships are not apparent. Concurrent with the ground motion studies, the underground structures program tentatively confirmed the design recommendations for corrugated steel structures when extended to megaton range devices. Concrete slabs showed greater resistance to high blast pressures than expected. However, further analysis is required before quantitative results can be determined. The radiation program produced the first successful documentation of integrated neutron flux as a function of range for megaton detonation. Analysis of fallout from megaton devices is still being conducted by the laboratories, and any conclusions must await the completion of this work. In the structural effects studies on the B-52, sufficient data were collected to substantiate a correlation between measured and analytical responses. This will establish a workable and reliable side-load computation procedure. For the A4D and FJ4, sufficient reliable data were obtained for correlation with response data obtained during Operation Plum Bob to permit subsequent defining of the high-yield weapon delivery capabilities of these aircraft. In the study probing the effects on a corporal fuse system exposed in a nuclear environment, it is concluded at this stage of the analysis that the system is electronically affected sufficiently to make its operation highly suspect. In the thermal radiation tests, it was found that a possible discrepancy may exist between Naval Material Laboratory's simulated thermal pulse and actual pulses. the data tends to reflect a lower effective radiating temperature for larger yield weapons. As in most of the experiments on hardtack, it is too early in the analysis stage to make definite conclusions. These must await further study of the great volume of data gathered.